Good morning, students. Let's continue the session with our next topic, that is Pauli's exclusion principle. Pauli's exclusion principle. Already we have noticed one point. A single orbital can be accommodated with two electrons, one spinning in clockwise, other spinning in anti-clockwise. The same was more clearly illustrated in this principle, according to which no two electrons in an atom has all the four quantum numbers. All the four quantum numbers as same. No two electrons in an atom possess all the four quantum numbers as same. Okay, let us illustrate this with some examples. Suppose if you take a first shell which has n is equals to 1, whose subshell is only 1, that is S subshell. S subshell has only one orientation, minus L2 plus L including 0, that is only one orientation, whose designation is S orbital. And this orbital can be accommodated with maximum two electrons, one spinning in clockwise, other spinning in anti-clockwise. Right? Now you compare these two electrons. This is one electron, this is another electron. So what are the quantum numbers of these two electrons? Let us observe. For the first electron, principal quantum number is 1. Second also principal quantum number is 1. Azimuthal quantum number is 0, same. Magnetic quantum number is also 0. But if you come to their spin quantum number, even though principal, azimuthal and magnetic quantum numbers are same, definitely these two electrons must differ in their spin quantum number. So in this way, one can illustrate that no two electrons in an atom possess all the four quantum numbers as same. You can take any picture. Suppose n is equals to 3. It has 0, 1 and 2 subshells. Under 0 it has only one orientation, 2 electrons, plus half and minus half. Under 1 it has 3 orbitals, px, py, pz, plus half and minus half, like this, plus half and minus half, plus half and minus half. Now under second subshell, orientations are minus 2, minus 1, 0, plus 1, plus 2. Each orientation is one orbital that can be accommodated with maximum 2 electrons. First electron is plus half, other one is minus half. In this way we already discussed. Plus half and minus half, plus half and minus half, plus half and minus half. Now, if you want to notice, suppose observe this first electron with this electron. Okay, you take positive clockwise spin only, this electron. See, consider those two electrons. What are their principal quantum numbers? Principal quantum number is same, 3. And what are their azimuthal quantum numbers? 0 and 1. Here itself it is finalized. If you consider electrons of different shells, in the second level itself they will be finalized. Different shells means first level itself it will be finalized. If you consider electron of first shell and electron of third shell, principal quantum number itself is varying. Obviously, their next quantum numbers also may vary. Suppose this electron, first electron with this electron, principal quantum number is 1, azimuthal quantum number is 3. Differed now. Here itself it is finalized. The next one may be same, but one value is differed. In this way, one can illustrate that no two electrons in an atom possess all the four quantum numbers as same. This was what given in Pauli's exclusion principle, which helps us in constructing an electronic configuration. See, when it comes to the electronic configuration of some elements in filling electrons in their degenerate orbitals. For example, you notice carbon 6. Carbon 6 electronic configuration. I hope you all practiced that electronic configuration using or with the help of a Moyle's diagram. So it's for your good sake only. Carbon 6 electronic configuration can be given as 1s2, 2s2, 2p6. Now let us start with the hydrogen once again. See, if you take hydrogen's electronic configuration 1s1. See, each orbital can be represented with a box here. That one electron is with clockwise spin, suppose, conventionally. Helium electronic configuration. Electrons are 2, no? So it is 1s2. So first electron is anyhow with clockwise spin. The next electron, which is also getting filled in the same, obviously should have anti-clockwise spin. Then only they get paired. So in this way, pairing of electrons takes place between those electrons having opposite spin. If both have same spin, they repel with one another and come out by releasing energy. Whenever there is a repulsion, a release of energy takes place. Okay, next lithium atomic number is 3. So it is 1s2, 2s1. So 1s2 is 1s is one orbital, 2s is another orbital. 2 electrons, one with clockwise spin, other one is anti-clockwise spin. This is conventionally, first we will take clockwise spin. When it comes to beryllium, 1s2, 2s2, the same way, first clockwise, anti-clockwise pairing, next clockwise, anti-clockwise pairing. Boron, 1s2, 2s2, 2p1, clockwise, anti-clockwise paired, next 2 electrons clockwise, anti-clockwise. P has px, py, pz, no. Now it is entering px. Suppose 2px electron has entered 2px. Now here the question is, in case of carbon, whose configuration is 1s2, 2s2, 2p2. In these two cases, there is no discussion possible because one orbital is this. Obviously, the next coming electron is getting paired with opposite spin. When it comes to 2p, the question is 2p1 okay, 2p2 is getting paired or going here. What's the case that happens? So 2p2 is, it gets paired or 2p2 in this way. Which is more possible? Which is more possible means to explain this. So which is more appropriate? To explain this, HUNDS had given a rule called as HUNDS rule of maximum multiplicity. According to this HUNDS rule, during filling up of degenerate orbitals, what's meant by degenerate orbitals? We studied long back. During filling up of degenerate orbitals, P or D or F, 2p has, any p sublevel has px, py, pz. Any d sublevel has dxy, yz, zx, x square, y square and z square. F orbitals also fx, yz, fx cube, fy cube, xz cube, like that 7 orbitals are there. So we are going to study about the higher levels in our mains and need sessions and followed by advanced sessions. Okay. Degenerate orbitals. During filling up of degenerate orbitals P, D, F, electrons start pairing only when all degenerate orbitals are singly filled. Means filled with minimum 1 electron. When all degenerate orbitals are filled with minimum 1 electron, then only pairing start. This was given by HUND. That's why it is called as HUND's rule. So, what's that HUND's rule states once again? During filling up of degenerate orbitals P, D and F, electrons start pairing only when all the degenerate orbitals are singly filled minimum. So, suppose now here 2p2 is the configuration. 2p2 means when we have 3 p orbitals which are equal in energy. This is suppose px, py and pz. Once again I am repeating and recapping that point. There is no such convention that px should be filled first or pz should be filled first, like that. 3 orbitals will be filled in a sequence, that's it. So 2p2 means first this electron will be filled, next this electron. Another orbital will be filled with single electron instead of getting paired. When pairing starts, let us see. Nitrogen 7, 1s2, 2s2, 2p6. So 1s2 as usual, first electron and second with opposite spin paired. 2s2 again, first electron and second will be opposite spin paired. It's not 2p6, it is 2p3. See, 2p3 means 1, 2, 3. This was not given in HUND's rule of maximum multiplicity. And next, when it comes to oxygen, whose atomic number is 8, configuration is 1s2, 2s2 2p4. Electrons are paired in s orbital, 2p4 means we have px, py, pz again every case. So 1, 2, 3, all the three are singly filled. Then as all degenerate p orbitals are singly filled, now the fourth electrons start pairing. This is with respect to HUNDS rule of maximum multiplicity. Okay, now oxygen fluorine 9. It is now simple. 1s2, 2s2, 2p5. So 1, 2, 3, 4, 5. Every time whenever such degenerate orbitals comes, first you fill single electrons, then only you start pairing. Okay, otherwise it may go to a mistake. Okay, that's why fill the single electrons and then start pairing. So this was given according to HUNDS rule. When it comes to some exceptional cases in writing electronic configuration, exceptional cases means anomaly. Anomaly was noticed in the electronic configuration, different from the predicted sequence. That's why the such configuration, as it is an anomaly, it was named as anomalous electronic configuration, also called as exceptional electronic configuration. So when it comes to the atomic number, suppose 24 chromium, atomic number 24 chromium. So let us write the configuration. I asked you already to practice that Moyle's diagram. So it is 1s2, 2s2, 2p6, 3s2, 3p6. How many electrons are filled? 24 means 6, 2, 2, 10 and 18. 18 were filled. More, how many electrons? 6 electrons are to be filled. And after 3p we have to fill 4s2, means 10 and 10. 20 are filled. More 4 electrons. As even though it is getting filled after 4s, 3d4, see, after 4s we have to fill 3d. This is proper sequence. The sequence is 100% correct. But as 3d belongs to third shell, you can also write this as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Both are correct. Don't get confused like 3d is filled first and then 4s. No. See the number of electrons. After completely filling 4s, then only 3d started filling. Understood? So the same mode of writing can also be presented in this way. If you have any confusion, you can proceed with that. But this type of shell-wise presentation always helps you. This all third shell orbitals are arranged at one place. See? And you are basically aware of the energy sequence. Energy of 4s is less than 3d, you people are aware of. But shell-wise electronic picture is also helps us in some cases. Okay, both are same. Now my question is, when this is the expected configuration for chromium 24, practically in practice, what was noticed? 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5 was observed practically. The arrangement of electrons in chromium 24 in practice was observed as 4s1, 3d5. And they had given a reason, that is due to symmetric electronic distribution. Symmetric distribution of electrons due to symmetric distribution of electrons. Symmetric distribution of electrons, which in turn is due to stability of half filled or completely filled electronic configuration. This is due to stability of half filled or completely filled electronic configuration. How, sir? How half filled means? What is the total capacity of D? D sublevel total capacity is 10 electrons. Half capacity is 5 electrons. They noticed that because of this symmetry, 3d5 means 1, 2, 3, 4, 5. Because of this symmetry, that 4s2, 3d4 is getting changed to 4s1, 3d5. because of the symmetric electronic configuration which is assigning stability to the atom. So this was clearly explained by using exchange energy concept. This was anomalous electronic configuration due to half-filled or completely filled stability was more clearly explained using exchange energy concept. Actually, when electrons are filled in this way, electrons with the same spin called as parallel spin also try to get accommodated. Electrons will be exchanged with the same spin, means they try to get accommodated with the same spin also in a single orbital. Electrons with same spin or parallel spin also try to get accommodated in each and every orbital, during which they repel with one another, as we discussed. And more such trials of parallel spin, more will be the repulsion, more is the energy released out. Atom comes to low energy state. Understood? You know that less the energy, more is the stability. Less the energy, more is the stability of the atom. So more the number of such parallel spin trials means, once again I am explaining you, suppose you take this 3d4, 1, 2, 3, 4. As we discussed, electrons will be filled first. Whenever degenerate orbitals are available, electrons will be first with the single electron each. Instead of this, even these 4 electrons also try to get accommodated. These two try to get paired. Some energy is released. Even these two also try to get paired. Some more energy is released. These two also try to get paired. Like that, this is another set of parallel spin. This is another set of parallel spin. And this is another set of parallel spin. How many sets of parallel spin? 1, 2, 3, 4, 5, 6 sets of parallel spin. More the sets of parallel spin that were trialed to get accommodated, more is the repulsion and energy will be released out. More the sets, more is the energy released out, which is called as exchange energy. This is all due to the trial of exchange of electrons having parallel spin to get accommodated in same orbital. So more the exchange energy released out during this, less is the energy possessed by the atom and more is its stability. So in this way, using exchange energy concept, symmetric distribution of electrons means why half-filled or completely filled orbitals are giving more stability to the atom was explained. So observe the same exchange energy concept in case of 3d5. In case of 3d5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 electrons. See, during the phenomena of attaining stability, electrons with parallel spin also try to get accommodated in every orbital. So when these two try to get accommodated, some energy released. Second pair of parallel spin, third, fourth. Okay, next. 5, 6, 7. 8, 9, and then 10. How many sets of parallel spins are there? See, 1, 2, 3, 4. 4 sets here. 5, 6, 7, 8, 9, 10. There are 10 sets of parallel spin. Here 6 sets of parallel spins. Suppose for each set of parallel spin, if K is the energy released, for 6 sets of parallel spin, suppose 6K is the exchange energy. 6K is the exchange energy. Already we discussed, more the exchange energy released out, more is the stability of the atom. Yes. When it comes to the half-filled configuration, instead of 3d4, when it comes to the half-filled configuration, how many such sets are possible? 10 sets of parallel spins are possible. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. For each set, suppose if K is the energy released, then exchange energy is 10K. So in which case more energy is getting released. In case of half-filled configuration, more energy is getting released. Means more the exchange energy. So more is the stability of the atom when it has half-filled configuration. In this way, the stability of half-filled or completely filled electronic configuration, atoms having half-filled or completely filled electronic configuration was explained using exchange energy concept, with respect to which the electronic configuration of chromium was practically observed as 4s1 3d5 instead of 4s2 3d4. Okay, likewise, some more elements also can be studied using this exchange energy concept. For example, if you take chromium, chromium finished, no, copper 29, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So how many electrons are filled? 10 plus 10, 20, 28, 20, 30. Copper is 29, so it is 3d9. It's not 3d10, it is 3d9. This is what expected electronic configuration. This is what expected according to Monel's diagram or energy of orbitals. But practically the electronic configuration of copper, in practice, electronic configuration of copper was observed as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. What was the practically observed configuration? 4s1, 3d10. This is also 3d10 means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has a completely filled configuration, whereas 3d9 means 1, 2, 3, 4, 5, 6, 7, 8, 9. It is not completely filled. As per the discussion exchange energy concept, just now we noticed that half filled or completely filled orbitals, as they are giving stability to the atom. So to attain such completely filled electronic configuration, copper electronic configuration is changing from 4s2 3d9 to 4s1 3d10. In this way, there are some anomalies which I asked you to observe from the electronic configuration you had written in comparing that with the given in the textbook. Okay, so this is how electronic configuration can be studied, and go through the configuration table given in NCERT textbook, right?